Okay, so hello everybody. Welcome to our Center for AI Innovation training sessions. Today, I'm very happy to introduce William Eustis, who is going to talk about data loading and tools in PyTorch and TensorFlow. William has been working with the center for, I don't know, a couple of years by now. And this is one of his favorite topics and in fact, one of the first projects he worked with the center was to develop a rather elaborate data loader for the video processing pipeline. And so ever since we asked him to give us a tutorial about this, because this is one of the topics that comes time and time again, and a lot of researchers have to sort of face this challenge of how to bring in the data into their models as a first step. So I'm very happy that William is able to present this tutorial today. And so William, please take it from here.
Absolutely. Howdy, folks. Welcome to, we'll talk a little bit about data loading. We'll also talk about some tools focused both in PyTorch and TensorFlow. Lucky for us, there's actually a lot of sort of topics that will relate between the two. So doing it in one often is the same way as we can do it in the other. So whether you're coding in PyTorch or TensorFlow or Keras or even JAX, these data loaders can often be sort of off to the side. You can pick your favorite one, do it in whatever method you want, and translate it to whatever task. Now, I know a lot of you are might need to build data loaders for specific applications. And so a large part of today will be talking about sort of making sure these data loaders are efficient, making sure we can figure out how to design these data loaders to work for some specific task, as well as just looking at other tools and other ways that people have done it in the past that we can sort of leverage and build off of. So, okay, let's go ahead and get started. Okay, as you heard from my introduction, my name is William Eustis. I'm currently finishing up my undergrad in computer engineering. I've been working with NCSA for, I think this is my third year. My focus is on computer vision and hardware accelerators. And I currently do research with NCSA and with Professor Kidrzanko. Okay, so our goals for today are to discuss loading data in PyTorch and TensorFlow. We'll talk about the importance, we'll talk about optimizations, and we'll look at some examples. Additionally, we'll talk about just some useful libraries and tools that I felt were relevant and important to discuss so that we can all save each other some time. All right, at a high level, when we discuss data loaders and data sets, we're referring to all of the steps that it takes in order to get data from wherever you're storing it to usually a GPU. Occasionally, maybe this is some other type of accelerator, maybe a TPU if you have the chance. Performing that computation, training our model, and then receiving new data as fast as possible, right? And actually, in many cases, loading our data as fast as possible can be and will be the major bottleneck of our training process, right? And so if we can accelerate how fast we can load our data by 2 or 3 times, then we can very quickly train our model for 2 or 3 times as long effectively, right? So, just naively, we can look at some data loaders like the ones below, right? So the one on the left, it'll take 3 minutes to actually iterate over some data set, just some example mini ImageNet that I pulled up. And then, just with one small change, changing the batch size to 128, we can accelerate this a huge amount. What is this? By a factor of 6. And then once again, by changing the number of workers and by pinning the memory, we can accelerate it by another factor of 2. So already, if you have this in your training loop, you can accelerate your training by a really amazing amount, 18 times just about. So, okay, we'll discuss what all of these mean in more detail and what you should be setting these values to in your specific use case. But without going too far ahead of ourselves, we'll talk a little higher level to begin with. So one thing that we just saw is just by changing a few hyperparameters, 3 numbers really, we can actually achieve a huge amount of performance gain. But with large data sets comes sort of large problems. If you have a custom data set, there was a data set I worked with in the past that was this light polarization data, and we had, I think, upwards of like 8 or 9 terabytes. And it was all stored on these distributed drives. And if you want to train a model on all of this data, you actually need to be able to load the data in efficiently and quickly, right? And this raises a lot of interesting problems, right? You have a huge number of files, meaning your system is having to make a lot of I/O calls in order to open and close files, which are expensive. You might have distributed storage. So some of your data might be on one drive that performs very well, and some of your data might be on another drive that does not perform very well. or has some high latency or low throughput or something. And maybe it's on just many drives. And how can we leverage that to the best of our abilities? We might need to have large bandwidth requirements. So especially if your model is sort of small compared to the amount of data you need to feed in, it's very difficult to feed GPUs as much data as they can process, especially when we have these clusters like HAL. It's very difficult to actually keep all of the GPUs busy. And so making sure our data loaders are as efficient as they can be can make sure that we're training as quickly as possible, that our experiments are working as fast as possible, and we can continue to iterate and continue to do science. And then additionally, there's even more complications, which is, it's not only as simple as sort of getting the data onto the GPU as fast as possible. There's these questions of how do we shuffle our data set? How do we augment our data set? Can some of these augmentations be done ahead of time? Some of these augmentations can't be done ahead of time. And so when do we do them? Do we do them on the CPU in parallel with the GPU? Or, maybe it's faster to move it to the GPU first to do these augmentations and then to also process it there. So there's a lot of interesting questions that we can start to talk about. But the first one that I'll sort of introduce, the best thing you can do to save yourself the most time is to get your data as close to your GPU or as close to your accelerator as possible, as soon as possible. So, this means if you have some, rotational disk, some hard drive, and you also have a SSD, you're going to want to store it on the SSD. Your I/O speeds are going to be much higher, your bandwidth is going to be much higher, and it means that you're going to be able to feed data as fast as possible. Now, that being said, if your data fits into your memory, if you have an entire cluster which has hundreds of gigabytes of RAM, and your data can fit into RAM, it'll be faster to load everything ahead of time once, and then to just immediately sort of pass it to the GPU when necessary. Now, okay, much more uncommon is you can fit the entire data set into VRAM, which is definitely by far the best. But this is pretty rare because we only usually have a couple tens of gigabytes of VRAM. And also the entire model needs to fit onto that. So usually that space is taken up pretty quickly. Okay, so yeah, some general rules of thumb. Also, we want to do our compute on our data as soon as possible. So, if we need to normalize our data, we want to maybe just store our data ahead of time normalized, right? And if we need to convert from like a float to an int or an int to a float, let's try to do that ahead of time so that we don't have to load our data, perform these necessary conversions, this necessary compute, and then also perform maybe random transforms, and then also perform our inference, right? If we can cut one of these stages off, we're just going to increase our bandwidth, right? Make each piece of data load faster. And then additionally, another sort of big format or another big factor here is storing your data in efficient formats. So this is just sort of a short list. Obviously, your data might be sort of complex for your case, but in general, storing your data in sort of these binary formats is going to be more quick to decode at the cost of potentially being much larger. So H5, I think, is a great example. If you have this massive data set, storing it in an H5 can be very efficient to take, especially to take slices. Say if you have a video and you need to take 30 frames out of the middle, these H5 or HDF5 file formats can be great for this task at the cost of being quite large, right? If you store it as an MP4, in order to get 30 frames out of the center of a 1 hour long video, you need to decode almost the entire video, which can be extremely slow and really hinder the process. Of course, this is maybe one of these classic examples of the more data storage you have, the faster we can sort of do things ahead of time, right? So storing your data in an efficient format can be really helpful for this. Okay, so let's start to get to some more specifics. When it actually comes to building these data sets, there's usually two major steps that we're going to take for any platform, for any language. The first one is just building our data set, and then the second one is going to be instantiating our data loader. The data set is just going to define, what is our data set? How do we get an example? What does the loading process look like? What is an example? And then the data loader is how do we actually get this onto the GPU, usually, hopefully, as fast as possible. Okay, in PyTorch and CAII, a custom data set looks like this. There's three major pieces. So there's the init function, which runs once when we initialize our class, the length, and the get item. So the init function we can imagine is sort of building up all of the work that needs to be done once. If we have, say, a folder of many files, maybe we want to keep a list of all of the file names, right? Maybe if all of these files fit into memory, we want to actually load all of these files once, store these in some, array, some list, and then we'll index into this list directly. Additionally, the length can return maybe somewhat obviously the length of our data set. Usually this is somewhat trivial to determine. If you have, for example, a folder of images, one image is generally one example. But this can be more complex. So an example I'll give is, natural language processing, for example, right? If you have maybe one large story, what is one example from this, right? Is it one word? Is it one sentence? Is it a sequence of 10 words that, sort of shifts over or convolves over the sequence? It's maybe not so trivial, right? Or, who says it needs to be 10 words? Maybe it can be 10 words, it can be 11 words, it can be 12 words. And then if you're doing, this mass language modeling approach, you sort of mask out a word and try to predict it. So, it really can't be non-trivial to determine what needs to be done in these. Of course, it does come down to each example, and we'll talk about a couple of them in a bit. But yeah, so let's discuss some of these. Before we start writing our own, I really, really encourage you to look if this has already been done. For most of the data sets that exist out there already. So if you're benchmarking some result, or if you're trying some new approach on an existing data set, there's almost certainly a data set that exists already. So in this previous example, right, we have a folder of images. PyTorch has this built-in general class, image folder, which you just pass it the folder of images, and it'll sort of figure it out for you, right? Each class being determined by the subfolder it's in, and then each file being a different example within that. Of course, there's more than just this image folder. PyTorch has built-in data sets for a huge number of different data sets and tasks. I think there's like 4 or 5 for optical flow data sets. There's probably like 10 or 20 for just classic image classification data sets, whether it be ImageNet, CFAR, SPHN, you name it. Additionally, I won't leave natural language processing out of this, even though computer vision is my background. This torch text library, which is sort of part of PyTorch now, sort of not part of PyTorch. Parts of it have been incorporated into the main PyTorch. Includes a huge number. I mean, this is just sort of the top 10, but a huge number of data sets for these common data sets that people will use in natural language processing. So, Ag News, Amazon Reviews, way down, you'll have things like Squad, you'll have things like even larger data sets, like I think it's called the Pile. These have data sets and data loaders even available online for efficiency. Of course, this isn't always an option. Very often we do have to create our own data sets because we have our own data and we would like to use machine learning in order to solve some problem that no one else has solved before. And so some useful questions that we can ask ourselves when we're creating these data sets is what is one example from our data set? Okay? What is maybe for, another way to think about this is what is my XY pair going to be when I feed this to my model, right? How can we represent these in an array efficiently? Of course, I say efficiently because we might not be able to load everything in an array or a list. And so we need to sort of do as much of the useful work ahead of time as possible in this init function. And that's this next part is what do we actually need to do in order to build this array? So let's say we have this example, right? We have this training folder. This might be somewhat familiar with what we saw previously, this image folder structure. But let's say we have this training folder. Within the training folder, we have a number of subfolders, one for each class. Within each class folder, we have a number of images, one for each sample from that class. Okay, how can we actually build this out? Well, we know that we're going to have to iterate over this for each class. The class ID is this for each image. Let's append the image in the class ID, right? Let's actually build this out sort of piece by piece and really build a functional data loader for this. So we'll keep track of the data and we'll keep track of the labels. We'll iterate over each one of our folders. So we have, some path, training folder, and then the class name. And we'll extract what this class name is. Of course, our model isn't going to predict, well, okay, maybe if you're doing some multimodal work, it'll predict a text. But in many cases, we need to convert this into an index. And so we'll just keep track of the indices like this. And if we reach a new folder, we'll append our new class to this folder. And then we can get the actual index for this class. So it'll 0, 1, 2, et cetera, et cetera. And then we'll just go one by one, and we'll append this tuple of the path to the image and the actual class ID for that image. Great. So now we've done a lot of this useful work ahead of time. We've determined that one example is one image, and its label is the class for that image. The next question is, what is the length of our data set? Well, of course, the length of our data set is the length of this self.data, with each one being a tuple of x comma y. And then finally, we need to do our get item function. And our get item function is just going to, because we've done a lot of this useful work ahead of time, it's just going to index into the self.data, get the image and the label. Of course, very often we do still need to load this. And so we can do like, torch.load, torch.load image. Torch Vision has their read image function. If you're doing a video, there's, read video. Don't forget, we might be storing this or it might be more efficient to store this as like some specific data type. And so if you're storing this as an H5 file here, we might be doing something like HDF5. Oops. HDF5, .load, and maybe we're indexing into it to get our specific example. Okay, great. So we've looked at sort of a quick example here. Let's talk a little bit more about like some more complex cases. So the example I'll give is, let's say that we have a folder with many videos of varying length, right? There's definitely some interesting questions that this brings up. So first of all, how do we generate, one training pair? What is sort of one example from this data set? With certain approaches, this definitely depends on your model. Maybe your model wants to consume the entire data set or the entire video. Maybe this is something that's important for our model's performance or important for how we want it to be used. Also, very commonly, it'll look at like a fixed number of frames. How do you sample these frames? Should they be consecutive? Should they be sampled uniformly from the video? Maybe the video is 30 FPS. Maybe this video is 60 FPS, right? If we want these 30 frames to be a fixed amount of time, then we need to keep this into account too. And so there's I think very quickly when we're working with these custom data sets, some very interesting questions can be asked in terms of what does one example look like? How do I want to process this? How can I do this ahead of time, right? Of course, if you're doing the sliding window and you want to say, hey, I want one example to be exactly 1 second of video, then you need to keep track of the video's FPS. You need to keep track of sort of a sliding window. You need to care about like this dilation. If this video, for example, is 240 FPS and we want 3 seconds, but we also only want 30 frames, then you need to be very careful about how many examples of this are there, right? We have sort of this one, then you shift it over by 1 frame, and you have here, next frame, next frame, next frame, et cetera, right? But then this also raises the question is, if this is an example, this top one, and then the next one just offset by 1 frame is another example. If we naively generate a train test split by just generating our data set and randomly selecting 20% to be our test set, we're quite obviously going to get some like pretty severe leakage here, or our model will be cheating, because it's essentially seen this example before, right? I'd seen it at least 1 frame before for all of these. And so we need to be, within our init function or within our get item or somewhere, we need to keep track of how we're determining our train test splits. One common way to do this is within the init function, we'll have this keyword train, and we'll let it be true or false. Apologies for the mouse handwriting. Takes some practice to get used to again. And if it's true, then we select the subset of videos. If it's false, then we'll select another subset of videos. If there's any questions, feel free to put them in chat. I'll make sure to address them.
Hey, William, can I ask something?
Sure, go for it.
Hey, so I really love your video example. I just wanted to highlight, I've been thinking a lot on like, how do you sample from videos when all I can really deal with are frames? And so one technique that just came out from Facebook last Friday in their Make a Video paper, this is where you can put in a sentence and they give you back a generated video. Their sampling technique was really interesting. I think it's the best I've seen so far. Is from YouTube videos, they choose a random FPS between 1 FPS and the standard 30 that all YouTube videos are in, pretty much. And then they sample like the first 16 frames, a set number of frames at that FPS, and that gives them different like motion speeds. Because if you sample at 1 frame per second, the motion will typically be faster, and if you sample at 30 frames per second, the motion will be slower because you're not seeing a longer period of time. And then they repeat that up to 3 times per video, so they have like 3 little sections of the video. I thought that was a really interesting sampling technique, and that's what I plan to utilize for my like general video pre-training of YouTube. So just really excited about that.
I haven't seen that before.
Yeah, if you have other recommendations, I'd love to hear them because I'm trying to implement this.
For sure. Actually, I just saw that sort of text to video on Twitter like 20 minutes before this. So it's cool that this is sort of big news. I'll maybe need to read it in more depth.
Yeah, it's a great paper. Absolutely.
So Cassim brings up a great point, which is how we actually determine this sampling can really change the dynamics. If you take a video and you choose to sample at 1 FPS versus 2, 10, 30, your model will really experience the very, very different data, right? And so especially if you're doing this pre-training approach, maybe there's this like masked autoencoders or scalable vision learners. I don't know the current state of the art for video pre-training. But in either case, if you're doing this pre-training, having different timescales is really valuable, maybe even a form of data augmentation that you sort of get for free. So really great points. And then another important factor here is, especially when we're working with these large videos, this example I brought up previously of this many terabytes, each frame was 3,000 pixels by 3,000 pixels. And at 60, or no, it wasn't 60, it was 24 FPS. The 60 FPS was a lower resolution. And for hours and hours. If we're randomly selecting individual frames, it's actually quite inefficient. Because from the computer's perspective, it's very much like we're doing random reads, which isn't always best. And so either storing our data in such a format that we're not doing random reads, or or just making sure that we're loading our data in such a way that we're maximizing our data bandwidth can really be pretty valuable. Oh, clip is for image pre-training. Yeah, okay, that makes sense. Yeah. So maximizing our data bandwidth can also be a really big factor with a lot of different data set types. I think videos in particular, it can be particularly problematic for, usually for images and text. We don't always have to worry too much about this, but it depends. Like high resolution images, for example, really have to worry about this. Okay, so we've created our data set for our problem now, whether it be text or whether it be images or whether it be our custom data set that works with data that no one's ever seen before. And we would like to make sure that we're getting it onto the GPU as fast as possible. We'll talk first about PyTorch. Right after, we'll talk about TensorFlow. But the PyTorch, the major tool that you're going to use here, if you're not using a tool, which we'll talk about later, which I really do recommend using a tool. One of these external libraries. They're quite fast. But if you just want to do it to begin with, you'll use a data loader. This data loader will take in your data set, which is just your instantiated data set class that we saw before. And we have all sorts of things that we can discuss. So batch size, of course, when we're loading data from our disk, how many things are we going to be loading at once? Obviously, loading many things at once can often speed up both training and it gives our CPUs things to do while the GPU is running. And so having a larger batch size, I think the general recommendation is, max out your batch size to whatever will fit on your GPU. But I think, I'm not sure if anyone knows if there's more recent research on this. I'm not sure. There's probably some like optimal batch size, since it has a lot to do with training dynamics. But usually I just max out my batch size and adjust my learning rate accordingly. Of course, shuffling your data set. Definitely shuffle your training set. I've run into many bugs before where I forgot to shuffle my training set. Your testing set, sometimes people like to shuffle, sometimes people like to not shuffle because you can sort of see different behaviors based on if you do or not. Of course, if you're taking, the average behavior across the whole thing for your test set, it doesn't really matter. It definitely matters for your training set. If you don't shuffle your training set, it can be difficult to converge sometimes. The sampler and batch sampler can be particularly valuable when it comes to distributed training. So especially if you're working on something like HAL and you want to be using all 4 of your GPUs efficiently, PyTorch has this data parallel, which just copies the model and the data over to all 4 GPUs, or splits the data, copies the model. This is definitely not the most efficient way of training. And in fact, the PyTorch docs say, don't do data parallel, please use distributed data parallel, which requires a lot more work. Each becomes its own process, its own training process. They have to share weights and all this, but it is really very, very efficient. Of course, this raises an interesting question, which is if we have sort of a disk here and a compute here, so this is disk, and this is what we'll just refer to as the CPU. This CPU is loading data, and it's going out to all of our different accelerators, or maybe there's multiple CPUs. We want to make sure that we're not sending the same data to all of the accelerators, right? We need to make sure we're splitting up this data evenly. And so, using this sampler and batch sampler, we can make sure that we're doing this distributed data loading efficiently without sort of redundant work, and especially without harming our training dynamics, which is like the worst case. A simple example I'll give is if you have, we'll say, poor sampling, and all 4 of your model copies get a bad example at the same time, your model will sort of immediately diverge a huge amount and very often be unable to converge again. There's these recent discussions of these people training these huge models. I think the Stable Diffusion, Boris Dayama on Twitter. And every 2 days he would have to tweet about how, oh, it got a bad example and the loss spiked, so I had to reset training to a previous checkpoint. I found this bad example. I've now removed it from the data set. So, especially if you're training on distributed computing, your data loading and things getting bad examples at the wrong times can be really quite harmful. The number of workers just refers to the number of CPU processes you're spinning up. I recommend this to either be 1 or 8, or the number of cores on your machine. Generally, I recommend the number of cores on your machine. However, there is some, we'll say, diminishing returns with this. So, generally speaking, the time it takes to load something will look like this, where your x-axis is your number of core or number of workers. And usually the number of cores on your machine is here. I think 4 or 8 just kind of usually works well. 1 is lazy, but sometimes it doesn't matter if your data is, we'll say, small enough. Okay, pinning memory, when we transfer our data from the CPU to the GPU, making sure it's aligned in sort of an unpaged section, make sure that this transfer happens efficiently. So pinning the memory can just make your .CUDA calls faster when it actually comes to transferring to the GPU. There's other things as well. So prefetch factor, if your CPU has extra time to load examples ahead of time, which isn't always the case, then you can tell it, I want you to load 2 examples ahead of time versus 3 versus 1 versus 0. Obviously, this is going to take up more of your RAM, but the benefit is it has more examples ahead of time. Okay, if you have any models that sort of take non-deterministic amount of time, I think auto-regressive models that can predict stop tokens. I've seen this a lot. Having a larger prefetch factor can be somewhat valuable because you'll get some training runs and some forward passes, backward passes that are quite fast. And if you get a couple of them in a row, very quickly you can sort of run out of prefetched data. And then you have this period where your GPU is doing nothing, which is always sad. Okay, TensorFlow focuses more on building out this data pipeline. There's some efficiency focused, we'll call functions, but there's also some more fundamental ones. So batch and repeat and map. After we instantiate our data set, we'll create this data loader in TensorFlow, and we can call .batch, which, as the name maybe suggests, batches our data. So that when we load something, we'll load, n items at a time. Repeat repeats our data set for some amount of times, and then map maps a function. So just as a quick example, we could maybe build out some function that converts some string to what we saw previously in our get item. So loads image, load the image, get the we'll just say return x comma y, right? So we have our data set, which is, we'll say a collection of strings. We map this load image function onto it. We batch so that, each sample is maybe 128 samples. And then we repeat our data set a number of times. Now, I will mention, of course, the order here definitely does matter. For example, if you batch and then repeat, and your data set is, we'll say, 64 examples, and your batch is of size 50, your batches will be, size 50 and then 14, and then 50 and then 14, et cetera, et cetera. But if we do this the other way around, so we repeat first and batch second, then it'll be, 64, 64, 64, et cetera, et cetera. With each of these batches, or sorry, 50, 50, 50. With these batches sort of striding across epochs, if that makes sense. 50, 50, 50. And then the last one will be, some like n mod 50, yeah. Just whatever's remaining. So the order of these definitely does matter. Of course, the map, maybe it's somewhat trivial that the order matters. Of course, mapping one function and then a second function will give you different results than the first function and the second function, or the second and the first. Okay, so this is straight from the docs on how we can optimize our TensorFlow data loaders. We'll talk about some of these in more detail, but at a high level, if you're working in TensorFlow and you want to make sure your data loader is fast, screenshot this, basically. Of course, these slides will be available too. But number one is prefetch. So, making sure you're prefetching your data. Don't wait for your model to finish its backwards pass before trying to load a new data. Make sure we're interleaving so we can load multiple copies of our data. In whichever time either data set is ready, we can provide that to the GPU. We can obviously parallelize almost everything with this num parallel calls. Make sure that we're mapping any transformations at good times, cache any transformations that we can to reduce having to load data every time. And we can also reduce memory usage using all of these. So let's look at some. So obviously prefetch is saying, hey, I read some data, it's ready right here. My model is going to start training. And while my model trains, I'll start reading the next sample, right? As simple as that. Of course, if this is not set to true, then we would not start reading this next example until after the training is done, which is not efficient. We can also interleave, open 2 copies of our data set. This copy, we start reading here, it's ready here. And then basically, anytime either of these are ready, we'll start loading that data next. This is particularly useful when we add this number of parallel calls, meaning, we'll open both of these data sets at the same time. We'll start reading from both of these data sets at the same time. And the moment one of them is ready, we can start training on it. And you can see just, already with this number of parallel calls, the amount of time your GPU is working is much, much, much higher, which is great to see compared to, these two approaches. Very often, we need to map some functions to our data set, whether this be a random transform, whether this be converting from a path to the actual XY pair. Mapping our data is often necessary. Of course, this can also be used with number of parallel calls. There's no reason we only need to be mapping one thing at a time. We have many CPU cores, right? Ideally, hopefully we have many CPU cores. If you're working with one, then I don't know, request some more. And then, of course, we can also cache. So if our mapping function is loading from string to XY pair, there's no reason to have to do this every time. Just cache, and that time, in the next round, when we try to request this data once again, we don't have to do it again. And of course, the order does matter. So if you need to perform some random transform, we don't want to, we'll say map and then cache, because this is just going to give us that same random transform that we got before, right? But if we split our random transform into a second map function, we can load string to XY, cache the loaded images, and then perform some random transform on the cached images. This way, we don't have this open and read downtime. We only have this map downtime. Well, really this transform downtime here. Of course, don't forget, we can still use number of parallel calls with this. So this really can get quite efficient using all of these together. Awesome. One moment. Wonderful. So another big part of this is TensorFlow also includes the TensorFlow profiling tool. So if you are working with sort of particularly high performance training pipelines, maybe you're using TPUs, or maybe you're trying to use like the entirety of HAL at the same time, it can be very valuable to use this profile tool to determine where the bottlenecks are and what you actually need to work on in order to make sure that we're actually utilizing it, right? Again, it can be quite difficult to feed data to a lot of GPUs and to keep them busy. And so making sure that we're finding the slowest part and making it not slow can be good. Of course, if you're using particularly large models and you're using this entire network, you might be doing distributed training. Hopefully you're doing distributed training. And so there's countless different packages out there that can help with this. Here's just a small list of them: PyTorch Lightning, Fast Forward Computer Vision, Torchbearer, Cornea is great for sort of 3D stuff. There's also PyTorch 3D. Detectron 2 has its own thing. It's an entire framework that can be used for like object detection. And so let's take a moment and discuss a couple of these. But before we move on, are there any questions about data loaders and data sets that I can address? Okay, excellent. So we'll go ahead and talk some more then. If there are any questions, just feel free to put them in chat and I can answer. So the first one that we'll talk about is this web data set. This is built off of PyTorch's iterable data set, although it is also compatible with TensorFlow. Again, with many of these data set focused stuff, you can use whichever data loader data set libraries you want. It just comes down to converting it in sort of a quick step into a TensorFlow tensor versus a PyTorch tensor. This stores all of your data sets as tar files, or some like edited version of tar files that are binary and really focused on like sequential IO and high performance. It's also focused on this nice TensorFlow like data pipeline operations, which I miss out on working mostly in PyTorch, as well as extremely easy multi-node training support. If you're using a really, really big data set, I really do encourage you to use this web data set. So this is the GitHub here. We can take a quick peek at it. It's quite long, so we won't look at everything. But if you want to do this multi-node data set, we can essentially just do it like by parallelizing everything right here, which is quite nice. It's just a single line of change to allow it to work with multiple different accelerators. They have multiple representations for your data. They have support for smaller data sets, big data sets, caching. They have really, really solid support for even storing your data on, Google Cloud or AWS with this nice like Unix like indexing. So, this is saying, hey, like I have 168 examples here, and I'd like to perform these augmentations on them, things like this. So this web data set can be quite useful. Great. The next one we'll talk about is Fast Forward Computer Vision. Of course, most of my background is in computer vision. This library is also super, super helpful for not only computer vision, but any sort of ML. Think of this as like a nice replacement for the data loader that we saw previously with PyTorch. This has sort of more low-level operations that they've built in from the kernel level even in order to really accelerate data loading. So it's a drop-in data loading system that really drastically increases throughput. It's compatible with PyTorch. It's compatible with web data set, which we just looked at. And it is specialized for computer vision. So they do have lots of very nice, handy computer vision transforms that also happen quite efficiently. But of course, when it comes to loading data, it needs to sort of be data agnostic, we'll say, right? One thing that I will mention is I think because this works at the kernel level, it doesn't work on HAL at the time, at least. I think at least a couple of months ago, there was still an issue with Power 9 support. Let's see if this is open. Okay, I guess not. Yeah, so I'm not sure if it's supported on Power 9, but still this, if y'all are working on other platforms or other hardware, this can be quite good to accelerate any training that you're doing there. Of course, one of the biggest ones that hopefully a lot of you are familiar with already is weights and biases in TensorBoard. These logging tools are really an amazing, amazing tool to help run experiments and compare results. Both are great. TensorBoard runs locally. Weights and Biases runs runs online. You upload all of your data to their website, and they have the nice plots for you. Personally, I use Weights and Biases. It's a little bit nicer for collaboration since it's hosted on their external server, and then also allows for some additional tools. They have these sweeps, I think is their keyword for them. Let's see if I can find it. Anything about sweeps? Okay, I won't look. Oh yeah, 2 and hyperparameters. So yeah, you sort of just run jobs and it tells, oh, training for this much dropout is the best, this learning rate is the best, this many epochs is the best, right? Things like this. And it's like really quite nice because it's all automated. Of course, there's more. I can open up my own Weights and Biases. And we can see just some experiments. This is some recent stuff I've been working on. There's a lot of examples for these, so they might not load too fast, but you can log whatever you want, test top 5, classification loss. We can see all the previous runs here. We can really easily filter through them too. Okay, I'll stop. Sounds like an ad read, right? Okay, there's also PyTorch Lightning, which is another great tool. Many of you who are working in TensorFlow are probably familiar with Keras, which is sort of a high-level API for TensorFlow. PyTorch Lightning is the equivalent for PyTorch. So it's Keras for PyTorch is how I would describe it. It reduces a lot of the redundant code you need to write, works with a lot of the libraries that we've talked about, Weights and Biases, Web Dataset. It's like agnostic to what accelerator you're running on. It supports lots of recent research. I've used it for model sharding a lot. Works well with distributed devices. It also has this sort of sub-library called Lightning Light, which reduces the training code even more, which is quite nice. So we can see, if you want to run on multi-node, really all you need to do is specify this num nodes, and it figures most of it out by itself. Low precision, you just need to sort of set this flag. Model checkpointing, early stopping, these can be like somewhat annoying and repetitive to implement ourselves. And they can be quite easy to implement with this library. So the only downside to PyTorch Lightning is that, obviously you do need to learn how to use it, which is always a non-zero amount of work. But, you can see they include all sorts of different operations and tools and things like this. So. Okay, I mentioned this just a moment ago, but Keras is the high-level framework built around TensorFlow. Very easy to learn, very easy to write, still supports every single operation you can imagine. It's fully functional. It's got everything you would imagine from a sort of a state-of-the-art extension for machine learning frameworks. You can do everything you want in Keras without even leaving it, and it's great. It's a great tool. Makes life easy for us, which is always good, And then the last one that I'll mention is this composer. There's this startup Mosaic ML, which is focused on efficient neural network training. This is nice because I think a lot of these things are sort of disjoint from things that we've talked about previously. So this allows you to apply some pretty state-of-the-art different approaches that accelerate training. So whether it be like model architecture adjustments or training adjustments or algorithms to perform data augmentations, you can really see some pretty massive speed ups in training speed on top of everything else that you're doing, right? So, if you're loading your data as fast as possible and the GPU compute becomes the bottleneck, the next question becomes like, how can I actually make my model train faster? Well, you can make the model smaller, which, isn't preferable. So how can we make it train faster while maintaining the same representational capacity? I think like Composer is one of the few things that actually does this well. Focuses on not making your model worse and still making it train faster, which is quite nice. Okay, I have a demo too, if y'all are interested, but I want to take a moment and ask some questions or answer any questions that you might have. Another particular, if you have any questions, like if you have a data set of a specific type and we want to discuss how we might build data loaders around that, I'm more than happy to answer things like that. Okay, we can talk a little bit about the demo then. Let me pull it up. Okay, I'll put this in chat too, just in case any of you want sort of a reference. But I think I'll spend the rest of the time just talking about this. Mostly what we do in this demo is explore different data loaders, explore how changing, prefetch factor, number of workers, batch size, whatever it might be, affects how fast we can actually load our data in. So it's mostly focused on this. Excuse me. There's also some interesting discussion at the bottom about creating custom data sets. So yeah, we can talk a little bit about this if there's interest. I think I also discussed, where is it? Yeah, so there's also an example of an iterable data set in PyTorch, which is a little bit different. It might be somewhat familiar with. We talk about these web data sets built off of the iterable data set, which instead of having these 3 functions, just include init and returns an iter.
So this is in collab. Do you have it in GitHub somewhere as well? Because this is in your collab, so it doesn't.
Oh, it's not shared. I thought I shoot. Yeah, I can maybe just upload the notebook. See if this lets me. Okay, there we go. Okay, so there's a Jupyter notebook. You might need to pip install a ton of stuff, or you can upload this to your own collab. But okay, I won't worry about running all these just because some of these can take a really long amount of time. But at a high level, we download this mini ImageNet data set. We convert it to a variety of different formats. So lower resolution, PNG, NumPy, PyTorch, arrays. And then the first example is just creating a data set for this. So we create our own. This one's quite easy, right? We don't really have too much work to do other than list out all of the different files. And then when it comes to actually getting an item, we can just get the file name, read the image, get the class ID from the file name itself, and convert that into a one-hot encoding, unless you want the class index, in which case don't do this, and returns that. We can benchmark how long some of these take. We can train a small model on it. We can see that, with a bad data set or a slow data set, this can take like upwards of 6 minutes. But once we optimize all of our different, data loader behaviors, we can train the same model in 1 minute and 27 seconds. So already, we're able to train the model 4 times faster, which is quite nice. We can introduce some image augmentations. Of course, this is going to really, somewhat drastically increase the time. Every time we load an image, we now need to perform all of these different element-wise or entire, image level different augmentations. And so now, instead of 1 minute 30, it takes upwards of 3.5 minutes to train the same model. Of course, the benefit being our model is now better. It's more generalizable, which is quite nice. And then we can also sort of create this data set that uses different types of files. So whether it be JPEG, PNG, NumPy, PyTorch, and we can measure the time it takes for all of these to run. With the TLDR being, these serial or these binary formats, the PyTorch and NumPy are going to be much faster to load. PyTorch being slightly faster, just because it doesn't need to do this extra conversion step from NumPy to PyTorch. With the cost of being quite large. There's no compression that's occurring when we're storing something as a PyTorch or NumPy array. But if it's stored as a PNG or JPEG, then they can be quite small, which might be a necessary cost sometimes, right? Okay, yeah, so we can train the model. Additionally, we can talk about potentially preloading some of these images. So if something fits into our data set, then we can load it ahead of time. And then when it comes to, instead of calling torch.load in the get item, we can call it essentially in the init function. This reduces our training time down by 30 seconds, which can be quite nice. What is that as a percent? Let's say 1/7 or 6/7 as long. Of course, this is just for images. This can work for different types of data sets too. So we have this moving MNIST data set, which is videos, with each example being a number of frames of a MNIST numbers moving around. We can perform this train test split as we were talking previously, making sure not to overlap examples. We write our get item function. We say, hey, I want this many clips or this many frames out of my example, and then extracting that from it. Selecting a random start frame and then selecting the next, n clips or n frames for the clip. And we can instantiate this and look at some examples and evaluate performance. And then there's also this iterable data set. This one's quite simple. I just sort of return a range. But these iterable data sets can be quite useful in a lot of cases. If your data is sort of, we'll call it like stateless, right? If you just need to sort of iterate and, or rather return an iterator that your model needs to train on. I think this is quite good with like sequences. An example I'd give is if you're doing natural language processing by hand instead of using one of these existing data sets, you can treat it as a sequence, and your iterator that you return is just an iterator of the different words or tokens that you need to train on. Okay, I think that's most of my discussion that I have with this demo. I can talk more in depth about anything if someone is interested, but otherwise, that's pretty much it. Thank you all for coming. It's been great talking to you, and I'll stick around with any answers to questions if you have any.
Well, thank you very much, William. Yeah, if anybody has any questions or concerns. Well, looks like there are no questions. Great. So we will post this notebook somewhere on our tutorials website, so this will be accessible there. But yes, otherwise, thank you very much for conducting this tutorial. This was very helpful to many to start to build their own data loaders. So thank you very much. I think we are done for the day.
Awesome. Thank you all for coming. I hope you enjoyed. If you have any questions, just let me know.